Welcome to the second lecture of the NPTEL MOOC on parallel algorithms. In the first lecture of the MOOC, we familiarized ourselves with the model of computation called parallel random access machine. We also saw an algorithm for finding the OR of n bits on the common CRCW PRAM. In particular, we had seen the variants of PRAMs like exclusive read, exclusive write PRAM, concurrent read, exclusive write PRAM, and various categories of concurrent read, concurrent write PRAM. So, we will take the discussion further now. Let us say we want to find the OR of n bits on a tolerant CRCW PRAM. So, let us say we are given an array of size n in which each location holds a bit. Let us say we need to find the OR of these bits. As we did in the case of the common algorithm, here also we take a location that we name R, in which at the end of the algorithm the result is supposed to hold, and then we proceed in this fashion. Initially, only processor 1 will initialize this location to contain 1. So, at the end of the first step, only the first processor has come forward and initialized the location to 1. So, R now contains 1. Then in the second step, all the processors that have a 1 will come forward, and processor 1 will compulsorily participate in the second step, irrespective of whether its bit is 0 or 1, and all of them will simultaneously attempt to write a 0 in R. R already contains 1, now all of them are attempting to write 0 in location R. Since this is the tolerant model, a concurrent write is merely tolerated. Therefore, if there is a write conflict, the content of the location will not change. So, in this case, the content of the location does not change. And then finally, in the third step, the first processor looks at this location and finds that the location contains 1 and its own bit is 1. Therefore, there is no further action taken. The answer of the problem is 1. So, what exactly are the processors doing here? So, let us look at the code of the algorithm. The algorithm proceeds in this fashion. In the first step, all the processors do not participate. This is a tolerant model. This is a variant from the common algorithm. In the common algorithm, all the processors together initialize the variable R to 0, whereas here only the first processor is initializing the variable to 1. This is because in a tolerant model, whenever there is a write conflict, the content of the location will not change. So, for the initialization to work, exactly one processor should initialize. Therefore, here we have only the first processor. So, this is at variance with the common algorithm. In the common algorithm, all the processors initialize the variable together, whereas here exactly one processor is scheduled to initialize the variable. After this, all the processors together in parallel will do this. If I equal to 1, then R is set to 0, which means the first processor is compulsorily participating. The other processors will join the first processor if their bits are 1. So, as we saw in the previous example, the processors sitting on locations 4 and 7, which are P4 and P7, will participate in the write. That is precisely because their bits are 1. Processors P2, P3, P5 and P6 will not participate because their bits are 0. Processor 1 is compulsorily participating, whereas the other processors are participating conditionally. They will participate only if their bit is 1. So, R is initialized to 0. So, these two initializations in fact are synchronous. Processor 1 and the other processors that are operating conditionally will be attempting to change the contents of R to 0 simultaneously. So, what are we achieving by this? We are checking whether there is any processor other than 1 that has a 1 bit. If at least one processor other than 1 has a 1, then all those processors will be attempting along with processor 1 to change R to 0. So, if there is a conflict at all, that is, if there is a 1 bit in locations 2 to n, then all those corresponding processors will be attempting to reset R along with processor 1. Then all of them will provide company to processor 1. So, this allows us to check whether there is at least one 1 in the range 2 to n. So, there are multiple cases. Suppose there is no 1 in the range from 2 to n. In this case, processor 1 will succeed in changing R to 0. So, R equal to 0 now indicates that the OR of the positions 2 to n is 0. Then in the third step what we do is this: if R equal to 0 and A1 equal to 1, we are setting R equal to 1, which means if R equal to 0 in any case, that is if there is no 1 in locations 2 to n, then the condition which will allow R to be set to 1 in the third step is the first bit being 1. So, unless the first bit is 1, R will remain 0, which it should, because in that case there would be no 1 in the array. To recap, if there is not a single 1 in the array, then in particular in positions 2 to n there is no 1. Therefore, there will be no company to P1 in the second step. P1 will be resetting R alone. Therefore, P1 will succeed in resetting R and R will end up being 0. Then in the third step, if A1 also happens to be 0, R will not be changed, R will continue to be 0, and that is what the answer is going to be. The second case is where there is at least one 1 in positions 2 to n, in which case in step 2 processor 1 is going to get company. There will be a write conflict. When there is a write conflict, the content will not change, the content will remain 1 that we had set in the first step. Therefore, at the end of the second step, R will be 1, indicative of the fact that there is at least one 1 in positions 2 to n. If R equal to 1, then we do not do anything and we come out. That is precisely how it should be. There is at least one 1 in positions 2 to n and the result is 1 indeed. Now, the third case is where there is no 1 in positions 2 to n, but the first bit is 1, in which case at the end of the second step we will have R equal to 0, and then in the third step we check the condition is R equal to 0 and A1 equal to 1. That condition is true, then R will be set to 1, which is how it should be. So, in the three cases, in all the three cases we find that the algorithm works correctly, and the total time taken by the algorithm happens to be order of 1. In step 1 only processor 1 operates, so it is an order 1, it is a one step operation. In the second step all the processors are participating, but every processor has only one write to do apart from one condition check. Therefore, the second step also can be executed in order one time, and the third step has only the first processor operating, and all that is done is a condition check and an assignment. Therefore, the third step also runs in order one time. In the fourth step, the return that is being performed will have to be performed only by the first processor. So, here this is wrong, only the first processor should be returning the value, or any one of the processors. This has to be conditional. It should be pardo for I equal to 1, return R. So, only the first processor will be returning the value. So, the algorithm works correctly in order of 1 time using n processors. So, on the tolerant model as well, we are able to find the OR of n bits in order of 1 time, exactly as we did in the case of the common algorithm. But as you can see, the algorithm is a lot more complex, and we shall see that algorithms on tolerant generally tend to be far harder to prove for correctness and to analyze than algorithms for common. Therefore, we will usually find that common is a lot more used in the literature. So, we have seen several varieties of CRCW PRAM models. How are these models related to each other? Is it possible to simulate these models on each other? That is, once we have designed an algorithm for one of these models, is it possible to run that algorithm on one of the other models with modifications? And if we do that, what exactly is the cost of such a simulation? So, that is what we are going to explore now. Let us say an algorithm runs on model A in t time, and suppose it can be simulated in model B in order of t time. Then we say that B is at least as powerful as A, and it is denoted in this fashion. It is read as B is at least as powerful as A. Since all CRCW PRAMs are similar except in their write conflict resolution schemes, we need to bother only about the simulation of the writes. That is, as we saw in the last class, each instruction of a PRAM consists of 3 phases. There is a read phase, there is an execute phase, and there is a write phase. So, consider an instruction that is to be run on model A, and let us say we want to simulate this on model B. The read phase can be executed exactly as it is, and the execute phase also can be executed exactly as it is, and a simulation needs to be done only for the write cycle. So, for the purpose of the simulation, let us assume that in a particular concurrent write of the simulated PRAM, processor I wants to write value Vi in location Mi. With this assumption, let us see how the models can be simulated on each other. First, I shall argue that the priority CRCW PRAM is at least as powerful as the arbitrary CRCW PRAM. An algorithm that is written for the arbitrary CRCW PRAM model can be run on priority without any change. This is because the arbitrary CRCW PRAM assumes that out of every conflicting set of processors, an arbitrary one will succeed, and the algorithm designer is constrained to assume that the identity of the succeeding processor will not be known a priori. That is, at the time of designing the algorithm, he or she would not have any idea of which of the conflicting processors is going to succeed. Therefore, the designer is supposed to deal with that uncertainty in the design stage. But in a priority model, that uncertainty does not exist. The designer knows that the processor with the highest priority is going to win. Therefore, the designer has a greater freedom on the priority model. Now, here we have an algorithm that is written for the arbitrary model. Therefore, the designer has taken on a greater constraint. The designer has assumed that only one of the processors will succeed, but has not assumed that any one particular model will succeed. Now, priority guarantees that. Priority ensures that out of every conflicting set of processors, one is guaranteed to succeed, and the succeeding processor is going to be the same one in one execution in execution after another. This is what is not guaranteed in arbitrary, but whatever arbitrary requires is provided by the priority model. Therefore, an algorithm that is written for the arbitrary model can be run on the priority model without any change. Therefore, priority is at least as powerful as arbitrary. Similarly, we can also claim that arbitrary is at least as powerful as common. This is because on the arbitrary model, the designer assumes that out of every set of conflicting processes, an arbitrary one will succeed. Common makes a stronger assumption. Common assumes that out of every set of conflicting processors, that is every processor in a set of conflicting processors is attempting to write the same value. This is a stronger assumption than in the case of arbitrary. When you take an algorithm that is written for the common model and run it exactly as it is on the arbitrary model, the algorithm will work correctly, because now the processors are all attempting to write the same value in every conflict, and one of them is going to succeed, and the succeeding processor is getting in the value that the other processors are attempting to write in any case. Therefore, an algorithm that is written for common can be executed on arbitrary without any change at all. Now we come to the collision model. I claim that the arbitrary CRCW PRAM is at least as powerful as collision. This is because a step of collision can be simulated on the arbitrary CRCW PRAM in 3 steps. So, the simulation is carried out in this fashion. First, every processor I writes the integer I in the location in which it wants to write. So, here first we are attempting to detect a collision. What we have is an algorithm that is designed for the collision model, and this algorithm we want to simulate on the arbitrary model. So, the simulated algorithm is going to run on the arbitrary model, and what we do is this: in the first step, every processor I writes integer I in cell mi. So, let us say we have a set of conflicting processors. Let us say P4, P7 and P9 are all attempting to write into the same memory location. So, in the first step, all these are attempting to write their own indices in this memory location. P4 will attempt to write 4, P7 will attempt to write 7 and P9 will attempt to write 9, all in the same memory location. But this step is being run on an arbitrary model. That is because we are simulating the collision model on the arbitrary model. Therefore, exactly one of these processors will succeed. Suppose 7 succeeds here, 4 and 9 fail. So, 7 manages to write 7 in this location. Now, if these processors read the value back, then they can know whether they have succeeded or not. So, processor 7 knows that it has succeeded, processor 4 and 9 know that they have failed. Now, why did they fail? They failed because they had a conflict. So, when they attempted to write a value, but find that the value written was something else, then they realized that there was a collision, there was a conflict, and some other processor succeeded in the conflict. So, 4 and 9 are now aware of the conflict, but 7 is still not aware of the conflict. When 7 reads back, what it sees is 7 indeed. So, it has succeeded in getting its right value. It could have succeeded because it is alone and did not face a conflict, or it could have succeeded because it was the lucky one in the conflict. So, except for processor 7, every other processor involved in this conflict knows that they have failed. Then in the second step, every processor that failed in the first step will write a special collision symbol in mi. So, 4 and 9 now realize that they have failed. They have failed because they were in a conflict. Therefore, in the second step, both of them will attempt to write the collision symbol in the memory location. At least one of them will succeed. It does not matter which one succeeds, but one of them will succeed. Since both of them are attempting to write the same value, which is the collision symbol will get inside. So, the location now contains the collision symbol. Now, processor 7, consider processor 7. Processor 7 succeeded in the first step. It could have succeeded because it did not face a conflict, or it could have succeeded because it was the lucky one out of a set of conflicting processors. It can find out which of these cases it was now. So, for every processor that succeeded in the step 1, let us read the location. So, processor 7 now goes to the location and reads it. It knows that it had succeeded in the first step. At the end of the first step, it had 7 in the location. It had managed to write 7 in the location. But now, when it looks at the location, it finds the collision symbol. Then it realizes that the symbol, collision symbol, appeared in that location because there were some conflicting processors which in turn came in the second step and wrote the collision symbol, overwriting the value which it had put in. Therefore, processor 7 now realizes that there was a conflict. Therefore, in the third step, what every processor does is this: every processor that had succeeded in the first step checks if cell Mi did not change its contents during the second step. If it did not change its contents, then that could be only because there was no other conflicting processor to change its successful write into the collision symbol. If there is no other processor, that is, had there been no 4 and 9, had processor 7 been alone, which means had it not been conflicting in this write, then it would have succeeded in the first step, and then when it reads its value back, it would not know whether it succeeded because it is alone or because it is the lucky one in the set of conflicting processors. But after the second step, when it finds that the value which it wrote still remains in that location, it would realize that there was no other conflicting processor to change its value to the collision symbol. Therefore, in the third step, it would go ahead and write the value it wanted to write in location Mi. So, in these three steps, therefore, a step of the collision algorithm can be simulated on the arbitrary CRC-W PRAM. What it means is that an algorithm which runs in t time on a collision CRC-W PRAM, an algorithm which runs in t time on the collision CRC-W PRAM can be simulated in 3t time on the arbitrary CRC-W PRAM, which is of the same order. Therefore, we say that arbitrary is at least as powerful as collision. And finally, we claim that collision is at least as powerful as tolerant. Given an algorithm on tolerant, let us say we want to simulate it on collision. So, let us consider the write cycle of an instruction of the tolerant algorithm. To simulate this on collision, we assume we have twice the memory. That is, the collision model is assumed to have twice the memory that the tolerant model has. Every cell of the tolerant model is assumed to have an auxiliary cell in the collision model. That is, one single cell of the tolerant model is assumed to have an auxiliary cell in the collision model. Thereby doubling the memory requirement. So, the processors that attempt to write in a memory location will first attempt to increment their corresponding auxiliary cells. So, to begin with, the auxiliary cells will contain some garbage value. It does not matter what the auxiliary cell contains. All the processors that want to write will first read the auxiliary cell of the intended recipient of their writes and then increment these values and write the value back. So, this value is incremented by all the processors. Now, this is happening on the collision model. Therefore, if there is in fact a write conflict, the value that is written will be the collision symbol. So, let us say this auxiliary cell contained 10 to begin with. All the processors that want to write in this location will read the contents, which is 10, and change it to 11, or they attempt to change it to 11. So, if there are multiple processors attempting to write in this location, all of them are attempting to write 11 here. But then because of the write conflict, they will not succeed in writing 11 here, instead they would be writing just the collision symbol. That is if there is a genuine conflict. But if there is no conflict, if there is only one processor attempting to write in this memory location, it will read the 10 that was there and write 11 instead. Therefore, when this processor looks at this location, it knows that it is not in conflict. But of course, there is a special case. We have to consider the case where the auxiliary contains the collision symbol -1. The collision symbol is nothing but a special integer. So, it is possible that an arbitrary location can contain the collision symbol -1 at any point in time. Therefore, if all the processors attempting to write in the memory location increments this value, then the location will end up containing the collision symbol. Therefore, even if there is no collision, we might assume that there is a collision. But this can be easily circumvented. A processor which attempts to increment the location first checks what value it has written. Here it has read 10 and has attempted to write 11. Similarly, if the value that it reads in happens to be the collision symbol -1, then instead of incrementing, they will attempt to decrement this value. Therefore, the value that is attempted to be written is indeed different from the collision symbol. Therefore, the processor knows whether it has succeeded or not. If it finds that a collision symbol has appeared in the auxiliary memory location, then it knows that it has failed and there is a conflict, in which case it would do nothing. The tolerant model is assumed to do nothing whenever there is a conflict. Therefore, the contents of the actual memory location, which is this, will be left as it is. On the other hand, when it finds a collision symbol, when it does not find a collision symbol, then that is a clear signal for going ahead and writing. Then the processor knows that there is no conflict and the processor will go ahead and write the value that it wanted to write. So, what this shows is that a step of a tolerant algorithm can be simulated on the collision CRCW PRAM in order of 1 time. Therefore, an algorithm that runs on the tolerant model in t time can be simulated on the collision model in order of t time. Therefore, collision is at least as powerful as tolerant. So, on the whole, we have shown that priority is at least as powerful as arbitrary, arbitrary is at least as powerful as collision, and arbitrary is also at least as powerful as common, and collision is at least as powerful as tolerant. In fact, we can show that all of the above relations are in fact strict. It can be replaced with strictly more powerful in each case. In particular, you can show that priority is strictly more powerful than arbitrary. This can be established by showing that for some problem P1, there exists an algorithm that runs in order of t time on priority, and by showing that for the same problem P1 on arbitrary, there is a lower bound of omega of t1, where t1 is omega of t, small omega of t, which means there is a problem P1 which can be solved faster on priority than on arbitrary. There is a lower bound proof which precludes an equally fast solution on arbitrary. Similarly, for the next inequality as well, we can find such a problem. There exists a problem P2 which can be solved faster on arbitrary than on common, and there exists a problem which can be solved faster on arbitrary than collision, and there is a problem which can be solved faster on collision than tolerant, which means all these inequalities are strict. But then how do collision and tolerant compare with common? This question becomes relevant because what we have just shown is that priority is more powerful than arbitrary, which is more powerful than common, and arbitrary is also more powerful than collision, and collision is more powerful than tolerant. But then how do common compares with collision and tolerant? It can be shown that common is incomparable with collision or tolerant. That is because there are problems P1 and P2 such that P1 can be solved faster on common than on collision, and P2 can be solved faster on tolerant than on common. So, there are two problems P1 and P2 that establish that common and collision tolerant are incomparable with each other. In this course, most of our discussions of CRCW PRAM algorithms would be confined to priority, arbitrary and common models. In particular, we will be mostly eschew the tolerant model, because the tolerant model is not known to have a nice property called self simulation. We would like our models to be self-simulating. A model is said to be self-simulating if a larger PRAM of that model can be simulated on a smaller PRAM of the same PRAM, the same model for a proportionate slowdown. We shall show that all these models are self-simulating except possibly for tolerant, and self-simulation is a crucial property. Since tolerant is not known to be self-simulating, we do not use tolerant much. We have seen a couple of algorithms on the CRCW PRAMs of common and tolerant varieties. Let us now see some problems on the ER-EW PRAM or CR-EW PRAM. Let us say we want to evaluate a Boolean circuit. A Boolean circuit is made up of the three logic gates AND, OR and NOT. Let us say we are given a Boolean circuit like this. And let us say we are given the input values. So, given this Boolean circuit and given the input values, we want to evaluate the output value. We know how to do this sequentially. We will evaluate the leftmost gates one by one. So, the outputs of the leftmost gates are solved one by one. Once these values are known, the second level gates can be evaluated. So, the outputs at the second level can now be calculated. Once these values are known, the third level gate can be evaluated and so on. So, this will require evaluating the gates in a certain order, in the left right order. A gate can be evaluated if both of its inputs have already been evaluated. So, sequentially we would require looking at each of the gates in turn, and the cost of the algorithm would be linear in the number of gates. So, let us say we want to evaluate this in parallel on an ER-EW PRAM. We assume that the gates have a fan in of 2 at the most. The OR and AND gates have a fan in of 2 each, and the NOT gate has a fan in of 1, and let us say the fan out of every gate is at most 1. That is, an output signal can be used by at most one input of another gate. So, in particular the output is not used at all. So, fan out could be 0 as well. So, let us say we are given a Boolean circuit of this form which is to be evaluated on an ER-EW PRAM. So, for the purpose of the evaluation, let us say we have as many processors as there are gates. So, let us locate one processor on each of the gates. So, for this example you require 8 processors. So, let us say we have one processor stationed on each of the gates, and then the gates can be evaluated in this fashion. Consider the leftmost gates first. The inputs to these gates are all known, therefore, their output values can be calculated simultaneously and in parallel. So, the processors that are situated on the leftmost column will all be active simultaneously, and they would produce their outputs at the same time. So, 0, this is 1, this is 1, and this is also 1. Now, once the outputs of the leftmost column of gates is ready, the next set of gates can be activated. So, the gates which are at the second level can now be activated. They would in turn be evaluated in the second step. All of them would be evaluated simultaneously. So, here we have a value of 0 and here we have a value of 1. Then the third level of gates will be activated, therefore, here we will get the value of 1. Finally, the fourth level of the gates will be activated and we will get a value of 0. So, in 4 steps we can find that the circuit evaluates to 0. So, in general, given a Boolean circuit on an ER-EW PRAM, we can evaluate the circuit in time that is equal to the depth of the circuit. but the total number of instructions executed is equal to the size of the circuit, which is the number of gates in the circuit. So, as you can see in the example we saw, the size of the circuit is much more than the depth of the circuit. The running time of our simulation is equal to the depth of the circuit, whereas the total number of instructions executed is of the order of the size of the circuit. The model is an ER-EWP RAM. This is because on none of the steps have we used concurrent reads and concurrent writes. Concurrent reads are not necessary because the fan out is at most 1. Therefore, an output that is produced will not be read by more than one gate. Therefore, there is no need for concurrent reads. And concurrent writes are also not necessary because all the values that are written are on exclusive lines. Therefore, the model is an ER-EWP RAM and the running time is equal to the depth of the circuit. Another problem that we can study at this stage is that of finding the OR of n bits on an ER-EWP RAM. Let us say we are given an array of bits and we want to find the OR of them. We can divide the bits into odd-even pairs. We consider the first bit and the second bit together. They form the first odd-even pair. Then these form the second odd-even pair. This will form the third odd-even pair. This will form the fourth odd-even pair. Then let us say we have 4 processors. Using these 4 processors, we find the OR of these pairs. So, here we find that the OR is 1, here we find that the OR is 0, here again we find that the OR is 0, and here we find that the OR is 1. So, we had started with 8 bits, now we are reduced to 4 bits. If we find the OR of these 4 bits, we would have the OR of the original 8 bits. So, the size of the problem has been reduced by a factor of 2 using 4 processors. We deputed one processor for each odd-even pair. Now, these bits are again paired off. This is the first odd-even pair, this is the second odd-even pair, and we depute one processor to each. The OR is found in this fashion. The problem size is now reduced to 2, but we have used 2 processors here. Now, there are only 2 remaining bits. They will form one single odd-even pair. With one single processor, I can find the OR of them in one step. So, here I have used one processor. The total time taken by the algorithm is 3. In the first step, I have reduced the number of bits from 8 to 4. In the second step, I have reduced the number of bits from 4 to 2. Then in the third step, I have reduced the number of bits from 2 to 1. So, the algorithm runs in 3 steps, and 3 comes from the total number of bits that we had. We had 8 bits and 3 is the logarithm of that to the base of 2. In general, if I had an n bit array, I could have found the logarithm of the OR of these n bits in order of log n time. And how many processors would I need to use? In the first step, I would need n by 2 processors. In the second step, I would require n by 4 processors, and so on. So, it would seem that I would require n by 2 processors to achieve a running time of order log n. So, when we have n by 2 processors running for order of log n time, the total cost of the algorithm is order of n log n, which seems exorbitant considering that the order of n bits can be found in order of n time sequentially. We shall see that a scheduling technique called the Brent's scheduling technique will enable us to reduce the cost of this algorithm from order of n log n to order of n later. We shall talk about Brent's scheduling principle in one of the future lectures. An analogous problem is that of finding the sum of n integers, which again can be solved on an ER-EW-PRAM in the same way. Suppose we are given 8 integers of which we want to find the sum. Again we can form odd even pairs. The sum of the first pair is 3, the sum of the second pair is 7, the sum of the third pair is 11, the sum of the fourth pair is 15. Then we have odd even pairs of 3, 7 and 11, 15. Here we have 10 and here we have 26. And finally, the sum of all the numbers is 36. So, in this fashion, for the same cost, that is order of log n time and n by 2 processors, we can find the sum of n integers in on an ER-EW-PRAM. The model that we have used is an ER-EW-PRAM because there is no concurrent read anywhere and there is no concurrent write anywhere. Another model of computation that we shall be using is what is called a comparator. A comparator is an apparatus that takes two values A and B and then produces the smaller of the two values on its upper output and the larger of the two values on its lower output. A network that is made up of comparators can be used for problems like merging or sorting. Let us say we have a comparator network for sorting. We shall study a couple of them later in this course. So, at this moment I am only asking you to visualize a comparator network. So, this network has several comparators interconnected in various ways. We have let us say a sequence of inputs flowing in and a sequence of outputs flowing out. So, if we provide a set of integers here, for example, these will be permuted in the output, so that in the output they will be in increasing sorted order. So, A3, A2, A1, A4 will be the increasing sorted order of these elements. So, imagine such a comparator network for sorting. The depth of this comparator network, that is the length of the longest path in this comparator network, will be the running time of the comparator network. That is, once the inputs are fed in, the inputs have to travel through the comparators and appear at the output. When they appear at the output, we would have them in sorted order. So, let us say d is the depth of this comparator network, which happens to be the length of the longest path in the comparator network. Then d would be the time taken by the comparator network to sort a sequence. I shall give an exercise for you. show that a comparator network of depth d and cost n. The cost of a comparator network is the total number of comparator units used in it. Can be simulated on an ER-EWP RAM of size n in time order of d. Of course, you can assume that one comparator output will be used only at one input. This assumption is crucial, but with this assumption, what you need to show is that a comparator network of depth d and cost n can be simulated on an ER-EWP RAM of size n in time order of d. So, with that we come to the end of this lecture. Hope to see you in the next lecture. Thank you.